Hello, community! A pure, powerful AI engine for games. Let's explore. Now, first step is, hey, what tokenizer would we need for a synthetic AI-generated video game? And currently we have SORA from OpenAI, and we have the joint embedding predictive architecture from Meta. And my last video also showed you how to update the technology components of SORA. But of course, we have here titans fighting. And I know what you ask. Hey, is there also Google? Let's talk about it. One new technology that is absolutely amazing is to optimize a vision transformer from a patch-level tokenization to a sub-object-level tokenization. And this happened just days ago. And you remember, if we take an image or a video, we have, I don't know how many million pixels, and then in the classical way, with a patch-level tokenization, we have 13 times 13 pixels or 26 times 26 pixels, and we create patches. But now the next step is to have sub-objects, but not just do a segmentation, no, have them as a tokenization step. So for my green grasshoppers, here is the easy explanation. If you're not familiar with patch-level tokenization, this text is for you. For us, we jump here to February 22nd here, and here a beautiful new technology from Hong Kong University of Science and Technology and Xiaobing AI, where they do exactly this. And let me, here, a little bit here of input, the sequence-to-sequence autoencoder for compressing the sub-object segment into the embedding vectors. And as those embeddings vectors are then fed as sub-object embedding into an LLM for vision learning. But let me give you an example. Let's start with the human language. It's much easier to understand from this perspective. Now, here I've written some text, and we have here the tokenizer playground. And you can choose here tokenizer for the human language. Let's go with GPT-4. And you see, our 434 characters are now 82 machine learning tokens. This is how the machine sees our human language. Please notice that quantum chromodynamics here, the abbreviation is now a Q and a CD, for example. 82 tokens. But we have a lot of tokenizers. For example, Llama 2 model, you see here, suddenly we have close to a 100 token. So this is a really different system. And you see quantum chromodynamics is completely chopped up here in little pieces, and we have a high amount of tokens. This is another way to build your vocabulary. The size and the mightiness of your vocabulary that you use in the AI system to predict here the next human word. But of course, we have much more modern system like Gamma. Gamma, you see, instead of 100 tokens, is 75 tokens. And this is now significant. But of course, this is related to the vocabulary size. Gamma has a vocabulary size of 256,000 tokens in its vocabulary. Llama 2 has only 32,000. Just have a look. For example, Gamma knows here quarks. Gamma knows here the QCD that Llama fills is in Gamma a known term, a known token, a single token. So you see, now we do the same what we did already in language, and now we just transfer it to the video sectors. Let's do this. So we have a sub-word level tokenizer. Let's go there. You see, quantum, for example, here, this is a word tokenizer. And if we go for sub-word tokenizer, you see this here, for example, with quantum. So what Gamma knows is just a single human word, quantum. They found that for particular reasons, sub-word tokenizers are really powerful. And now we transfer this here to a sub-word, a sub-object, a visual object level tokenizer. Let's generate this image. You can say, hey, build me an image of a car with a Ferrari 456 body, 456 wheels, and 456 doors. You see, the complete word-level tokenizer or object-level tokenizer would be Ferrari, and then you would have the complete car. But if you go sub-object, you can specify exactly what you mean. A new idea to have a tokenization in the image and video sector. Now, you can say, hey, Ferrari 456 door, and you get this. Or you say, you forget, say, hey, without the sub-object token, left side door. And then you say, here you have your Ferrari, but exactly the door is missing, since it's now a sub-object token. So you see, a complete new technology, beautiful, but so brand new that nobody implemented it till today. But you see what's happening now in video technology. Great. What is amazing, imagine we have here text to video, text to image, and you say, hey, Ferrari 456 door, but now in the material wood. What would be the visual subtoken for this text? Well, easy. You get now here exactly this door segment in wood, and it even takes care here that here in the frame you have some wood inserted too. So you see, tokenizers are extremely important here, especially in the very early phase when you define the objects that you're going to work with in your AI system. So build your image with sub-object token, build your video or your games with very specific tokenizers. Let's have a look at this. You know this. This is the famous video from OpenAI, SORA, this night walk. But do you know what's missing? Do you know what we are going for now in this video? Yes, of course you know. So, SORA, beautiful. The joint embedding for predictive architecture. At first it was by Meta just for image. Now we have it for video without a text, but anyway. And now, since a few days, we have from Google GENIE. And you see where I placed GENIE before I really read the article from Google, the publication. I thought, hey, this is similar something to what Meta did. We have some unsupervised learning of video materials. However, if you jump here into this article, February 26, 2024, GENIE, Generative Interactive Environments, you say, hey, wait a minute. So it is not like SORA where I have a text to video. Now, I have an interactive system where an agent can move around in a predefined system. What is beautiful, you have as an input different option. You have a prompt, beautiful. But you have, for example, an image. You need one image, or you have something drawn by your children or by whatever. And out of this single image, GENIE is able to produce a playable video game that is absolutely in the environment that your first real-world photo or text-to-image generated photo is. So whatever you have as an input, you will play in this environment. And you might say, how is this possible? How on earth is this possible? So we're at the very first development stage. So we only have an 11 billion free trainable parameter system. They call it GENIE, and they consider it a foundation world model. More about this later. What are the components? We have a spatial-temporal video tokenizer, an autoregressive dynamic model, and a simple and scalable latent action model. I will explain all of those in 5 minutes. We make now a step from some SORAs, a synthetic video generation, where you have a prompt, and you see this woman here in the night walk in Tokyo or Kyoto, I don't know. You have a synthetic video. But now you want, it's already 1 week since it was published, to have a synthetic interactive environment created from out of this. So how you do this? Well, that's quite a lot of technology, but what is interesting is, imagine we were talking about interactive environments. In our AI models, in the simplest case, we had a room. This is here, this gray area. And then in blue, we had an agent, a person running around in the room. A very simple game, extreme simple. And then we have an object 1 in green and an object 2 in red. And then we have interactive points where you can, I don't know, pick up a sword or move an object or whatever. You know, this is the simplest thing you can imagine. And now an AI should generate this. So let's have a look at this. And the more I read about GENIE, I thought, wow, this is really covering here the whole spectrum. And then I understand, wait, if this is really learning to have interactive environments, this is the correct ordering. This is definitely above the other two. So, beautiful. And now you know what's missing. Now, what I want to do, I want to click now here on my controller or whatever, or I want to say, hey, lady, now please go to your left or turn around or enter the next street on your right-hand side. You want to have an interactive control, maybe voice control, maybe you have a controller from your Playbox or PlayStation or whatever you have. So you see what we're looking for. We want to have SORA, the level of a synthetic video, but now interactive, that we can steer video operation. And this is GENIE. GENIE, and let's start from the beginning, because this should be a very simple video that everybody can understand what's happening in technology today, utilizes here a new and novel video tokenizer. But we use some old technology, so it's simple to understand, and extract some action, some latent action, via some causal action model. And then both the video tokens and the action tokens are passed to a dynamic AI model. No game engine, nothing, pure AI, which auto-regressively predicts the next video frame or the next image using here a MaskGIT Generative Image Transformer system. Now, if you are not familiar with this, MaskGIT or Mask Generative Image Transformer, here we have it February 8, 2022, so this is more than 2 years old already. This is a very powerful tool that we use. If you're not familiar with it, this is a beautiful scientific paper on arXiv to read and inform yourself about it. And again, we have a very clear analogon what is happening in the language modeling and what is happening now in the image and video modeling. We use the same idea. So, you know, in language we have BERT. And BERT introduces here a mask language modeling task to learn here language representation. And we use here normally a bidirectional self-attention in our BERT system that allows the mask token in our MLM to be predicted utilizing here context from both directions, our bidirectional BERT system. And then we have our sentence transformer built on bottom of this, and so on. Now we do the same. We take the same idea, and now instead of a BERT system, we use now a vector quantized variational autoencoder, and we do now here the same with images. And of course, we have to go to a specific mathematical space that we construct where our mathematical operations are much easier to perform, are faster to perform. And it's a two-stage process. In the first stage here, which is known as the tokenization, and now you understand why I'm focusing so much on tokenizer, it tries to compress the image from the pixel space into a discrete new mathematical space we call a latent space, and primarily consists here of 3 single steps in the first step. We have an encoder, we have a codebook, and then we have a decoder. And you notice this is an old technology system. And at the second stage, it first predicts the latent priors of the visual token using here some deep autoregressive model. You're not going to believe it, it's a transformer model. And then use the decoder from the first stage to map the token sequence into image pixel. So we go from our artificial mathematical space where we do the calculation back to the pixel space. You notice, this is 1 year old. If you don't feel familiar, this is a very simple video for you, where about a year ago, I showed you if you're going to go from autoencoder to denoising to convolutional variational autoencoder to vector quantized variational autoencoder, and then jump from them to the diffusion process, this is the video that explains the idea and a little bit of code behind this, if you're not really sure if you understand everything about it. Beautiful. But now let's talk about this MaskGIT, or this Generative Image Transformer system. Now, very easy, also a two-stage design. Again, we have here tokenization. So we have an input image of two penguins. Beautiful. And then we have a tokenizer that tokenizes the image into our visual tokens. And then, we have here an encoder, and with a decoder, we do the reconstruction of this. So you see here in our new mathematical optimized space to do here very beautiful mathematical operation. So not to operate in a high dimensional pixel space, we use here this particular latent space for an accelerating computation. And now the second step is here for MaskGIT, a bidirectional transformer model that we apply. And it performs something that we call a mask visual token modeling. We have here our mask token, and then with a bidirectional transformer that learned this on a lot of training data, it is now able to predict here the tokens from this mask token system. Here in green, you have a very simplified explanation for my green grasshoppers, for my younger community members. Beautiful. Okay. Again, in the language, I showed you with BERT here the mask language modeling, the MLM task for language representation learning. If you want to see this in code, I have this video for you where I show you how we pre-train here a BERT system, and then we build our own S-BERT system, our own sentence transformer. Now here with the Generative Image Transformer, it's almost the same. Designing new image synthesis paradigm utilizing parallel decoding and bidirectional generation. For the second stage, the authors of MaskGIT propose here to learn a bidirectional transformer, just showed you. And now instead of here the mask language modeling that we use here identical tool, the mask visual token modeling. So you see, this is why the token and the tokenization is so important, and why I started with tokenizer. Because you build or break your system with the right visual tokenization system. Great. Yeah, for my green grasshoppers, if you are not familiar here with the vector quantized variational autoencoder, here's a short information, and of course you have to know vector quantized generative adversarial networks. Beautiful. So now let's come to GENIE, and I make it very simple. At first, being simple, we make a further simplification. We do not go for the complete full-fledged power of a vision transformer. We do here a little bit of a simplification. We use an ST transformer. Why? Because it is faster to compute, it is more memory efficient, and it is also real good for the task at hand. If you want to know what is an ST transformer, it contains here a number of spatial-temporal blocks with some interleaved spatial and temporal attention layers. So self-attention, beautiful multi-head self-attention, everything, followed again as in the vision transformer by a feed-forward layer as standard attention blocks. In the self-attention and the spatial layer, you can have now the calculation. What is so nice now, that the computational complexity goes not or scales not with the quadratic here of the context length, but it scales linear with the number of frames. You see, a simplification that Google makes here, but is absolutely the perfect technology for the first step. So we go here in a simplification from a vision transformer to a more memory efficient ST transformer architecture. If you are not familiar with ST Spatial-Temporal Transformer, you see here, this is a beautiful publication from Leibniz University Hanover and the University of Twente from August 2021. So we know this system. This system is around some time, but it is also very active. And I have here the latest publication here, February 22 from 2024, about Spatial-Temporal Transformer for radar-only segmentation. And yes, you guessed it, we have here the University for Defense Technology. So you have an idea what we are talking about. But it is still, we use it, and it is still a lot of research going on in this particular field. But now we want to use it for a civilian case for a game AI. Let's have a look at this. Yeah, this is it. This is our ST transformer architecture. And as I told you, we have here the spatial attention and we have the temporal attention, and then we have our classical feed-forward layer, and we just have a linear computational complexity, as beautiful as can be. Now, if Google tells you in a research paper that they have, although they have multiple clusters of TPU, even the version 5 TPUs, they trained dataset 30,000 hours of internet gameplay videos. And they focused only on two-dimensional gameplay videos to be starting point. 30,000 hours to bring into your compute system and do the computation. Even for Google with GENIE, this is quite intense from the infrastructure. And also they have some huge TPU tensor processing unit clusters. Even Google says, hey, we start simple, beautiful. So GENIE consists now of 3 simple modules. The first, I told you, the video tokenizer. This is why it's so important. If you say, hey, tokenizer is boring, it is important that we choose the right one. Then, as I told you, I want to click here on this lady in the dog walking here somewhere in Tokyo. Click, and then she moves to the right side, or she enters a coffee shop, or she takes a taxi. Whatever you have on your controller for action that you can do, you want that this action here is learned by the system. What we have is only the video. So we do not have that at, 2.4 seconds into the video game, the user presses the button up or down or jump or run or whatever. No, nothing. We only have the video material without any instruction at all what is happening. And the latent action model now learns from the frames of the video what action is possible in this environment and what action was chosen by the user who was playing the game. Because remember, this 30,000 hours of training data is just that you film more or less, you record here the video game itself. So now you know this, and then you're not going to believe it. We just put it together. We have here our video tokenizer. We have here the action that is going to happen here. And then you just build a dynamic model to go from one video frame to the next video frame if a specific action like jump or run or stop or turn to the left happens. This is how we build our interactivity into the video games. Beautiful. Now in reality it is a little tiny bit more complicated. So let's have a look. The dynamics model is simple. This is our decoder-only mask generative image transformer system that we know that we love. And it simply utilizes here a cross-entropy loss for training like all our other systems like we know here from language training. So it takes in the video tokens and the action embeddings, jump, run, whatever, and predicts here the future mask video tokens. Beautiful. If you have, for example, here a ball and you press up, you expect that in the next video frame, the ball has a new location in your video frame, preferably on the trajectory upwards. Great. So we know how to do this with this technology. The video tokenizer is also an old friend. So we convert now the raw video frames, our images, into discrete tokens, reducing here the dimensionality, as I told you. Maybe you should use here a topological reduction mechanism. And yeah, in the simplest case, Google uses here a vector quantization variational autoencoder and incorporates the temporal dynamic of the system through here a simplified ST transformer, improving upon solely the spatial compression methodology. And just to give you an idea how long it takes just to find here a tokenization, Google said, hey, this took about 3 days on our TPU cluster. So you get an idea for a two-dimensional, simple game, low resolution. There's a lot of computation to do. But now we know the technology. Now we know how it's happened. And then left is only, how the hell does the system learn the action? So how does the system know what button or whatever you click on your video controller so that the ball jumps up or right or whatever? So we have to infer this action between the video frames in an unsupervised manner. There's no text for you to help, nothing. So what you do, you facilitate here the controllable video generation. You encode your action into a small discrete set of codes using here again, what a surprise, the vector quantized variational autoencoder based objective, allowing here for a future human control. Because when the system is learned, and it knows exactly what actions are possible if you give it a specific image, then it just will feed forward it to the dynamic model. Beautiful. So talking about training, how you train the system, because it has 3 elements, so it's a little bit more tricky to train it, to pre-train it. 2 phases. Follow the standard autoregressive video generation pipeline methodology. First, and again, focus on the video tokenization element. First, which is used for the dynamic model. You see, yeah, it goes in the dynamic model. And B, Google co-trains here the latent action model directly from the pixels and the dynamic model on the video tokens. Of course, it has to understand what is happening between the different video frames in sequential order. Beautiful. Now let's have a look at all 3 elements in a little bit more detail. On the right side in green, for my green grasshoppers, you have the very easy explanation. And on the non-green side, you have it a little bit more precise if you want to do this and code this. So, the tokenizer. We know what is our tokenizer methodology. Unfortunately, it is not a technology I showed you right at the beginning, because it was just days after Google published GENIE that Hong Kong University came out with this beautiful new video tokenization. But okay, here we still have to go with a vector quantized variational autoencoder with an ST transformer architecture. And you know, we compress video into discrete token to reduce the dimensionality complexity and enable a higher quality, faster processing, better mathematical formula. Yeah, you use it. Yeah, absolutely. We have here the frames of video generating here discrete representation of each frame. It's the size here of the discrete latent space, and the tokenizer is trained using here the standard objective over the entire video sequence. So beautiful. Easy. Yep. Incorporate the temporal dynamics in the encodings, which improves the video generation quality. Yes, exactly what I told you before. Now, the latent action model, this is a little bit more tricky. Remember, we have just watching a video. We don't know who pressed what exact button, up, down, whatever. We have to deduct the action that's going to happen. So the system is learning in a given scene what action can happen, what did happen, and what are theoretical possible, which is a much nicer question, but more about this later. So, to achieve a controllable video generation, we condition each future frame prediction on the action taken at the previous frame. Such action labels are rarely available in videos from the internet. An action annotation, if you ask a human being, hey, watch this, and then you type in here, now this happened, and now somebody pressed up, and now somebody pressed down, this can be costly to obtain. So you need here an AI system. So the system itself learns here the latent action in a fully unsupervised manner. The system learns it by itself. Beautiful. Please be careful. At first, of course, we start with a limited number of possible actions. Let's say you sit in front of your TV, you have your controller in your hand, and maybe you have 4 or 8 different switches you can tap on. So we restrict ourselves now the number of predictive action that you can press up, down, left, right, whatever, to 8. Very simple, just 8 actions are possible in this video game. And how you do this, and now this is the beauty of the variational autoencoder, you just limit the vocabulary size of your vector quantized cookbook. Remember, this is step 2 where I explained this to you. So the maximum number of possible latent action is now defined into a small value to permit human playability and further enforce controllability. So let's make it simple that the system can learn this in the very first iteration. Great. But note, this entire LAM system, this latent action model, it just learns here and helps the complete system to train to understand what actions do we see in this video game. When LAM learned each and every action, we don't need it anymore at the inference time. And now, if we have inference time, we expect the user, so I want to click now here on the video of SORA and say, now go to the left side, or now go to the right side, or enter now a taxi. Of course, instead of clicking, you would like to have voice commands, but this is about a later video. Beautiful. Okay. Now we jump back to the 10,000 miles view. What are we talking about? And here we have now a classification. What is the wording given to training data? Okay, so you know everybody is currently talking about world models. Make it simple, the training data for those AI systems that everybody calls in a different way, and there's a complete mixture and complete chaos, and everybody tries to be hype with marketing slang. Let's make it easy. If you have a video and you have actions defined in your training data, you can build a world model. And your controllability is based on each different frame. On a frame level, you can have jump up, jump down, whatever. If you have a training data that has a video and a text, like think about SORA, you are on a video level. You have a text prompt. You say, generate a beautiful video of a woman walking in the night in Tokyo and it's raining. Those class would be, to be precise, only a video model, but not a world model, since we have no action integrated into this. And now GENIE is above all of this. I mean, Google is brilliant, and I'm amazed that they came up with this research and they published it. So imagine what they already have in their technology pipeline. Yes, and then they do things in the implementation that makes me wonder. But anyway, GENIE now is here. The training data are just recordings of videos. They just recorded, they filmed a video without any action given in addition, without any text given in addition. This system is learning from videos. Now imagine you do not take a video game, but you take a YouTube video in 3D. You have an idea where we are going with this technology. You don't have a video game that has artificial environments, but why not go in the real Tokyo nightlife scenario in this particular street that really exists with the real shops that are there just 2 days ago? Okay, but let's stay here. Yeah, so if you hear world models, video models, beautiful, yeah, now you know a little bit. It is about the training data. And GENIE does something beautiful. We do not need action. We do not need additional text. GENIE does this and learns from videos. So imagine if GENIE would learn all Google videos from YouTube. Yeah, what you could do would be amazing. Okay, so Google says, hey, we propose GENIE, a new form of generative AI that enables anyone, even children. You know, children can draw an image, and then GENIE would be able to, from this single drawing of a child, to produce a video game in exact same environment. and step up into generated syntactic worlds, as we can with human design simulated environments. So GENIE can be prompted to generate a diverse set of interactive and controllable environments despite training from video-only data. Now have a look in the future. As you can see here, we have a YouTube video, somebody just recording walking through the streets of Tokyo, Shibuya. Now imagine you would feed this into GENIE. GENIE would understand what people are doing. People can go up staircases, down staircases, people can enter coffee shop, buildings, people can talk to each other, people can interact, people wait before crossing the street, cars are driving by in a certain particular pattern. You see, you can have an AI system that learns just by watching videos. No game engine you have to program to build with a human. The AI is able to completely understand all the visual information, but of course, the TPU clusters you would need would be massive. Even Google is saying that on a two-dimensional level, they have computational restriction because it is so complex. But from the technology point of view, there are no limitations. It just costs a lot of. But companies that are worth trillions of dollars, I don't think that this cost will hold them back to generate virtual AI interactive environments in our future. And this is not just for creating game AIs, but imagine if you want to train an astronaut for their mission to Mars. You can also have here specific synthetic training environments to train the astronaut how to behave on Mars. You can build this out of an AI system without any human interaction at all if you have enough training data. So you see, there is some amazing technology development happening right now. Almost every day we have new technology coming up, being published, being integrated. And I think now is the time you have really to watch this closely, because the complexity, how companies are integrating new technology and existing technology, like vector quantized variational autoencoders and to build new AI system. So I think the future is gonna be amazing. And here you have it, GENIE, the first of its kind, a generative interactive environment created purely by AI watching videos. No human instruction, no human annotation, no human action descriptions at all. The system learns just by watching us. I hope you enjoyed it. I hope it was informative. It would be great to see you in my next video.